have a little warm-up for you. I like to do a little math from the real world, and for many of you, this will be your real world next week. I am talking about Thanksgiving. As I mentioned, we're not going to be here, but I have a little advanced prep for you. So, you know, you're going to be having Thanksgiving dinner probably, and you're going to be eating lots of food, and afterwards, it's traditional to take a nap or maybe a walk around the block. Well, my question for you was, if you really want to get rid of all those calories you just ate, how far would you actually have to walk? And I'll show you a very useful mathematical technique to figure this out. But to start off, I went to a website that would let you know approximately how many calories you're going to eat. So I tried to select a fairly traditional Thanksgiving dinner, and we'll see how many calories this is. So I'll tell you what I chose to see if this sounds appropriate for it. I picked a glass of wine during dinner, if you're 21 and over, of course. I picked a cup of coffee afterwards, a few potato chips to munch on before it starts, a salad with ranch dressing, of course. We have turkey, you have to have that with stuffing, cranberry sauce, mashed potatoes and gravy, and a roll with butter. And afterwards for dessert, I have pumpkin pie for you with whipped cream. All right, so how many calories would that be? Well, according to this website, 1,915 calories for that meal. So, let's say you're going to take your walk around the block afterwards. Well, let's see how far you're going to have to walk to get rid of that. So what I have for you, I found a website that said approximate rate at which you burn calories, and I have it on my math cam for you. What it says is if you walk about 3 miles an hour, that's a decent pace actually, that's a 20-minute mile, so that's not a slow walk, you would burn about 0.027 calories per pound per minute. And what I wanted to show you, this is a rate, that word per is a tip-off for that. You can handle these with simple little fractions, and if you just watch the units, those will guide you into what arithmetic you need to do. So sometimes people get confused, like, oh, I have this number, do I multiply, divide? I don't know how to get to my final answer. Just let the units guide you. So I'm first going to make a little fraction out of this rate that I found on the web. So that word per is your guide. That's where basically your fraction bar is going to go. So it's 0.027 calories per, and we have per pound and also per minute. So I'll put both of those on the bottom as if they're being multiplied. And the first thing I want to do is let's go ahead and get a rate just for you of how fast you would burn calories taking a walk at this speed. So you would put your weight here, and I'll just pick, we'll pick an approximate random person here. We'll say there's a 150-pound adult. So if you were 150 pounds, for example, all I would have to do is multiply by 150 pounds. And I'll show you why I knew to multiply here. All you got to do is watch the units. I'm actually going to cancel units out when I do these multiplications. So just like with fractions with numbers, I have pounds on top, pounds on the bottom. They are canceled out, and then I'm left with calories on top and minutes on the bottom. This is going to give you a calorie burn rate for yourself. So you would multiply 0.027 times 150, you will get 4.05. And now look at the units that are left on that. That's going to be the key to proceeding. Calories on top, minutes on the bottom. So this is in effect your burn rate. What we want to do is see how long it's going to take you to burn off your entire meal if that was your goal. So that was, remember how many calories that was? It was 1,915 calories. I think that's more than you're supposed to have in a whole day or something. I don't know. Anyway, we'll go with it and see what happens, okay? So 1,915 calories you want to get rid of. So what we're going to think of this is I'm just going to convert this. I want to convert calories to minutes. And so you got to think about, okay, how would I get rid of those calorie units and introduce minutes? So what we want to do is multiply by a fraction. So I'm going to say, okay, times a fraction. I want the calories to cancel. So I need to put those on the bottom so they'll cancel away. And I want to be left with minutes. So I'll put minutes on top. So all you have to do is put in a fraction here that you know is equivalent. And we just wrote this rate for ourselves. Right up here we said, okay, your burn rate, 4.05 calories for every 1 minute you walk. So the arithmetic here shows you're actually going to divide. You have a 4.05 on the bottom and a 1,915 on the top. So this solves your problem of, you know, do I multiply, divide? I don't know what to do here. So we are going to divide. We won't need this previous rate information anymore. And if you divide this out, you get 473 minutes. That's a little walk for you, right? Well, how many hours is that? Well, we can do the same process to figure out how many hours this is as well, as long as you know a rate to convert minutes to hours. And we do. We know how many minutes are in an hour. So take your 473 minutes there and multiply by a fraction again, and just say to yourself, okay, I want minutes to cancel, so I'll put those on the bottom. and I would like to keep hours. And all you got to do is fill in your fraction with something that you know is equivalent. And I know that 1 hour has 60 minutes in it. The minutes will cancel. You'll be left with hours, and the fractions show you need to do a division. So 473 divided by 60, you get about 7.9 hours. Okay, I don't think you're going to walk for almost 8 hours, but just to finish my little warm-up here for you, let's say you did. How many miles would that be? We can answer this too, again, with the same process, because we have a rate for how fast you are walking. At the beginning of this, I said this was all for a 3 mile per hour walking speed. So let's find out how far that actually is. Take your 7.9 hours. I'd like to get rid of hours, so put those on the bottom. I'd like to be left with miles. So put in a fraction that you know is equivalent. And we just mentioned that you were walking at a speed for every 1 hour. You're going to walk 3 miles. That's 3 miles per hour. That shows you that you are going to multiply. 7.9 times 3 gives you 23.7 miles. All right, now that seems a little crazy, right? You have to walk almost 24 miles to get rid of your Thanksgiving dinner. Well, the truth is you burn calories through your day-to-day activities. So just moving around the house, you burn some calories, and just your heart pumping burns some calories. But after a big meal, you may want to burn some extra ones. A walk might not be a bad idea. Or maybe you could take it easy next week. Or you could choose to ignore all this and just have fun next Thursday and, I don't know, worry about it in your nap afterwards. Well, just for fun, that was our math. Just for fun, I have some turkey trivia for you. This is not mathematical, just for kicks, okay? The poultry industry, which involves turkey and chicken and others, makes 2 to 4 billion pounds of feathers every year. I have a picture of one of these culprits. You can see all of his feathers on my computer here. But my favorite trivia fact for you, there is an electric plant in Minnesota that generates electricity by burning turkey droppings. In fact, here is a guy sifting through them right now, and look how happy he looks. So he is thrilled to get these droppings ready for the power plant. They burn 700,000 tons of turkey droppings a year, and they generate enough electricity for 50,000 homes doing that, and they use up 40% of all the turkey droppings in Minnesota. The rest of it goes for fertilizer and other goods. I don't think it's wasted, actually. So I'm wondering if it's a little smelly, but it's definitely very ecological, I suppose. A couple other little bits of trivia for you, just for fun. Some statistics here, a few numbers. Traveling. Many of you are going to be traveling next week. So what's the busiest travel day? I always hear Thanksgiving, busiest travel day of the year. Well, if you watch the news, they will show you the airports the Wednesday before, and they will say that's the busiest day. It is for air travel. That is true. In fact, they estimate 27 million people are going to board planes next week, and that will fill 90% of the plane capacity. So that's quite a few. That's 4% more than last year. However, most people actually travel by car. In fact, 91% of the people travel by car. If you factor that in, the busiest travel day of the year is actually Thanksgiving Day, right on Thursday. 91% of those people in their cars, a lot of them going on Thursday itself. One last bit of trivia for you. It is also one of the busiest days for plumbers. And why would that be? I don't know what you're thinking. No, it's because a lot of people put stuff down the kitchen sink they're not supposed to, like grease and fat, and it clogs the pipes. So if you're cooking a turkey, don't put your grease down the drain. You have to call the plumber. He won't be happy coming on Thanksgiving Day, right? But what I was going to tell you about is a little bit about what's called a false positive. And I don't know if you've heard that term before, but for example, let's say you go get tested for a genetic disease or something, and they run a test on you and they come back and they say, okay, you've tested positive, that means you have the disease. How sure are you that you really do have it? Should you go get a second opinion, for example? Well, it turns out sometimes in some situations, it may not be as much of a positive result as you think. So we're going to do a hypothetical situation here. And by the way, most medical tests are not 100% accurate. They usually give some measurement. So we're going to make up a hypothetical situation here. Let's say you are testing for some genetic disease, and it's 99% accurate. That means if you really have the disease and you get tested, 99% of the time it'll tell you correctly you have it. But also if you don't have it, well, 99% of the time it'll correctly tell you that. 1% of the time, it'll be wrong. All right, so instead of getting all caught up in fancy math theories, we're just going to do a sample city, okay? Let's say we have 100,000 people in a city, and let's say the disease is in 0.5% of all these people. So it's not too common a disease, kind of a rare disease. Let's see what would happen if all the people in the city went to get tested. All right, so I have
the summary here on my little math chem, we have a half percent rather of the population actually has the disease, and the test is 99% accurate. We're just going to keep tabs on our population and see what happens. So we're going to start with 100,000 people, and all of them are going to go to the doctor's office and they're going to get tested. So of these, let's see, well, we'll decide how many actually have the disease first. So that's a 0.5% actually have the disease. So how many people is that? Well, if you take a 0.5% of 100,000 people, it only comes down to 500. So 500 people running around the city actually have the disease. That means the rest of them don't. So this is 99.5% don't have the disease. And if you multiply that percentage out, you get 99,500. So all we've done so far is we split our population according to who has the disease actually and who doesn't. Now, assuming that no one knows whether they do or not, they're all going to go get tested. So let's see what the test would actually do to each of these people that go in. So let's take the people who actually have the disease, and we're going to have two different results here. Most of them, in fact 99% of them, are going to test positive because the test is doing what it's supposed to. So testing positive, 99%. If you take 99% of 500 people, you get 495 people. So 495 people correctly test positive, and they find out, okay, unfortunately you do have this genetic disease. But what about the others? Well, there are some that are going to get a false, or rather they have the disease, they're going to get a false negative because, well, 1% are going to get an incorrect test result. So they're going to test negative, and that leaves a whopping 5 people. All right, now we're going to do the same thing with the other group, okay? So let's take the ones who actually don't have the disease. This is 99,500. Let's do the same thing to them. How many of these will test positive? Well, if they test positive, that's an incorrect result. It's a false positive. So that's 1% because, well, the test is 99% accurate. If you take 1% of 99,500, you get 995. All right, now the others are going to test negative. That's what's supposed to happen. That's 99%. And if you take that percentage out, it's 98,505. All right, so I'm going to scoot this over a little bit. Here's your results. Here's how everyone's going to test and what their real status is. You know, they don't know their real status, but we're pretending that we do. So the question is, if you tested positive, are the chances that you have the disease 99%? Because, I mean, that's what most people think, that the test is supposed to be 99% accurate, right? So if you go to the doctor and he says, or she says, you tested positive, and they say, okay, well, 99% chance that's right, I guess I have it. Let's see what really happens. Well, look at the positive test results. There's 495 here, and there's 995 here. In fact, if you look, these positive test results, the 995 are incorrect ones. These are from people who actually do not have the disease. There are more people testing positive incorrectly than there are actually testing correctly positive, which means if you get a positive result, there's a better chance that actually it's wrong than you actually have it. In fact, we can figure out the exact percentage here. If you look at how many people tested positive, there's 995 here, there's 495 here. So how many of those really do have it? Well, we're going to do a simple little ratio here. So actually have the disease, we know 500 do. Of those that tested positive, it's 495. So if you tested positive, 495 people, actually, it's correct. You have the disease. But the others, well, if you look at how many people actually tested positive, there's 495 plus 995. If you figure out this fraction, it comes out to be about 0.332. That's 33%. So 33.2% of positive test results really have the disease. The other 66.8 don't. So this idea of a false positive, it actually can be very misleading when you hear 99% accurate. Now, I should give you a couple disclaimers because, I mean, is this realistic, you might want to ask. Well, if you look at medical tests, many of them are more than 99% accurate. In fact, some of them are 99.998% accurate or something. So that improves things. And also, this becomes much more dramatic if you have a rare disease. If you were testing for something like, I don't know, if you did a random drug test to see if people had alcohol at dinner last night, you know, you get a much higher response. Well, then it's much less dramatic, and in fact, it would be much more accurate. So it's with a rare disease and one where the test is not perfect, but fairly accurate, you still can get these skewed results. Now, another thing I should tell you is if a lab testing your blood or whatever tests positive, oftentimes the lab themselves go test it a second way to make sure before they tell you bad news. So this is a little bit hypothetical, but you can see when the math works out how misleading it can be if they just say, oh, the test is 99% accurate. And today we do have something for you, very interesting, and it is inspired by a new addition to the Mathline family. Our producer Bill and his lovely wife have recently given birth to their first child. So may I present the television premiere of Erin Marie, 15 days old today. There she is. Isn't she cute? Here's another couple pictures for you. And finally, nice hat, I think. This is her Elvis impersonation. Beautiful. So what are we going to talk about today? Well, we're going to talk about how babies get their eye color. So we're going to talk about a little bit of genetics. And I actually have a picture on my little computer of a bunch of eye colors. And this is a little bit of a disturbing image, all these eyes staring at you. But you'll see a whole assortment from blue to sort of greenish and hazel and down to very deep brown. So what determines how you get your eye color? And you know, genetics is a funny thing. It's very interesting if you actually learn a little bit about it. If you had no notions of it at all, you might think that if your father had brown eyes and your mother had blue eyes, that you should have some mixture, some in-between color. But in fact, that's not the way it usually works. So usually the children have pure brown eyes or maybe pure blue eyes. So how does that happen? Well, it turns out it's a little bit complicated. There are several genes that control the eye color. But we thought we'd show you kind of a simplified version here because there has been work done that shows this is basically how the genetics are working. And in fact, there's some famous people who pioneered work with flower colors, and they showed how this basically is operating. So we're going to take a simplified view. We're going to, for the moment, ignore green and hazel. So don't mean to leave anybody's eye color out, but just make things simple. We're going to stick to blue eyes and brown eyes. And it is true that brown eyes are considered a dominant gene over blue eyes. So here's the weird part. All of you guys have 2 copies of the gene in you. And if you decide to have children someday, you're going to contribute one of those. So how does it determine whether you have blue or brown? And specifically what we want to look at is if your parents both have brown eyes, what are the odds you could come up with blue eyes? Or is it inevitable that you will have brown eyes as well? So we have a little animation to show you how this would possibly work. And sorry to our producer, we've replaced our producer and his wife with with models. So sorry. So anyway, here's Mom, and here's Dad. And if you look, we had some letters written there. And the big B is representing brown, and the small b is representing blue. And each of these parents have one of each gene. Now, because brown is dominant, they have brown eyes. Now, let's say they have a child, and by chance, they both contribute a brown gene. Well, there's the lovely child, brown eyes, of course. Now, there are other options, though. The mother could contribute brown, the father blue, and the baby gets one of each. But remember, brown is dominant, so even though the baby is carrying one of each, the baby shows brown eyes. Similarly, the mother could contribute a blue and the father a brown. Again, the baby gets one of each. Well, blue is not the dominant one, so blue does not show up. The baby will have brown eyes. Or finally, there is a fourth possibility that each parent can contribute a blue gene, and in this case, blue eyes will show up on the baby because there's no brown dominating gene. So where's the math in this? Well, it's interesting to look at what is the probability that if your parents have brown eyes, you could possibly have a different color. Most people would think if your parents both had brown eyes, well, you're going to have brown eyes. So a little disclaimer here, as I mentioned, this is a little bit oversimplified, so this is not absolute fact we're giving you. We're giving you the general idea of how these kinds of things work with genetics. But also, the only way it would be possible at all is if your parents were carrying, at least one of them, a blue gene. So the interesting thing we notice here is that if both parents have brown eyes and they were coming from those gene backgrounds, it is possible to have a blue-eyed baby. In fact, I have a more official version on my math cam here. This is kind of what you'd see if you actually saw an article on genetics. So we have a little grid. This is called, I believe it's called a Punnett square, if I'm saying that correctly. And this is generally what they do to decide how the possibilities are of what the offspring might have. So what I have is on top I have mother, and I have brown and blue options. And remember, every human has 2 copies of each gene, one you've gotten from your father and one from your mother. So in this case, the father, again, has these same combinations. So we saw in the animation there was a chance of 1 out of 4 in this scenario that you would have blue eyes, even though both parents had brown. Well, just for kicks, let's shake this up a little bit and see what another option might be. Let's say the mother has blue eyes. Now, from our little model, the only way that would happen is if she was carrying both blue genes. So we'll make this mother a blue and a blue, and we'll make the father a blue and a brown. Now let's look at all 4 options, and we'll see what the odds are that the kids have brown eyes, let's say. So if the father contributes a capital B, which is brown, and the mother contributes a lowercase b, which is blue, here's the option. You have the same option for this square. You have 2 lowercase b's for this square and 2 lowercase b's for this square. So if you look here, if you have 2 blues, you are definitely going to have a blue-eyed child there. So there's blue and blue. Now if you have one of each, remember brown is dominant, so the brown kicks in over the blue, and you will have brown eyes on these 2 options. So it turns out, in this case, you would have a 50-50 chance of blue eyes versus brown eyes. That's because the father had one of each. The father could have had 2 brown rather, which would be the capital B there, and in that case the odds would be completely different. So you really would need some knowledge of what the parents were carrying to figure out the odds of what would happen with the children. But the interesting thing is, if both parents have brown eyes, it could be that all 4 kids they have, or let's say have brown eyes, and then the grandchildren, all of a sudden a blue eye shows up out of nowhere. And this could happen, several generations down the line, because we're always carrying these dominant recessive genes, and sometimes, well, it takes a little while to show up. All right, so I don't know, I think the genetics is pretty interesting if you've ever learned a little bit about it, but there's a little bit of probability for you, and a little tribute to our newest Mathline fan, Erin Marie, 15 days old.